Welcome to Bite-Size Data Science. In the last video, we talked about ensemble models for classification and regression. This time, we discussed logistic regression. For one thing, the name logistic regression is kind of a misnomer since it is not used to create regression models, but instead to create classification models. The regression part comes from the fact that it gets results through a parameterized formula and returns a probability as the result. Let's take a quick step back and look at linear regression. You may remember this type of graph where we plot values in an XY axis. In this example, we have the weight of a vehicle as the X variable and the miles per gallon as the Y side. A linear regression model represents the line that best fits the observed values. For a two-dimensional problem, this can be represented by the formula y equals a times x plus a displacement b. Given a value of x, or the weight of the vehicle, we can estimate the miles per gallon it can achieve. The way to find the right formula is to limit the overall error between the formula and the observed values. Logistic regression starts with a general linear regression formula like the one shown here that generalizes to the following formula, which accommodates as many attributes as we need. The result of the linear regression formula is not the logistic regression. To complete the formula, we have to use what's called a sigmoid function. In this formula, x represents the value of the linear regression. Without going into more details, the result of a logistic regression is a probability of a specific class. I'd like to make a few observations before going through an example. First, we quickly discussed the use of logistic regression for binary classification. It is possible to use logistic regression to solve multi-class problems. Second, we can see similarities between logistic regression and neural networks. Both use linear regression formulas. Both also use nonlinear functions. In the case of logistic regression, we see the sigmoid function, and in the case of neural networks, the ReLU function is usually preferred over the sigmoid one. Maybe we can consider logistic regression our gateway model to neural networks. Let's get into a notebook and see how we can use logistic regression. I am using the IBM Watson Studio environment to run my notebook. If you are interested, you can find a link in the description on how to create a free account on that platform. Links to the notebook I am using here are also available in the description. The data I'm using is coming from the University of Wisconsin. I first heard about it in the book Data Science for Business. The data is used to predict a cancer diagnosis of benign or malignant. We can take a quick look at the statistics for each attribute. For example, look at the differences between area mean and smoothness mean. It is pretty obvious that they are not operating the same scale. That reminds us that we will need to pre-process the data. We extract the columns we want to use for training and evaluation. Obviously, the ID column is not a characteristic of the data. We also identify the target value, the answer we are looking for, as the attribute diagnosis. As mentioned earlier, we need to make sure all the attributes are in the comparable scale. This is easily done using the scale method from sklearn. Looking at the result of a scaling, we see that the standard deviation is now the same for all attributes. We are ready to create and train our model. We use the LBFGS algorithm to solve the linear regression formula inside our logistic regression classifier. This is the default choice in sklearn. A few other methods are available. There is no need to go into the details of these algorithms here. The model created by sklearn includes several attributes. Here are a few of them. We see the identified classes, the order of importance, as we'll see shortly. The number of iterations tells us how many times the algorithm adjusted the weight or coefficients of the training attributes. I also show the intercept value, that is basically the value returned if all the attributes have a value of 0. Let's look at a few predictions. The predict method gives us the classification prediction. If we want to see how confident the prediction is, we can look at the probability of these predictions. The prediction is basically created based on a specific demarcation line from the probability. By using the probability instead of the result, we can easily adjust model predictions by selecting a different demarcation value. How accurate is our model? We can use our testing data to figure it out. In our case here, we got an average accuracy at over 98%. There is one additional attribute the model includes that can be important in understanding the model. We're able to retrieve the weight used in the linear regression formula. The greater the absolute value is, the more impact an attribute has on the result. Finally, here is a quick try on creating the model using different linear regression formula solvers. We see that we end up with the same accuracy for all, but with a different number of iterations to solve the problem. There are more parameters we can adjust when creating a logistic regression model. For example, the defaults are not appropriate for all the solvers as we just saw. This video gave you an introduction to logistic regression. At this point, you should have a good idea about how it works. You should also be more comfortable with its usage. See you next time on Bite-Sized Data Science, and don't forget to subscribe.